In the last lecture, we have familiarized ourselves with some symmetry conditions relating to the Fourier coefficients. We would like to continue this discussion with an example where we make use of the symmetry conditions and use them to calculate the various Fourier coefficients quite effectively. Consider this example where we are dealing with an f of t which is a half wave rectified sine wave of amplitude a and a fundamental period t naught. Now when you look at this waveform does not have either an even symmetry or an odd symmetry. You recall that we had observed earlier that any given function can be split up as its even part and odd part respectively. In other words, if you have an f of t, if you break this up as f of t plus f of minus t divided by 2 plus f of t minus of f of minus t upon 2, this becomes the even part and this becomes the odd part. Because when you change t for minus t, the value of this part remains unchanged. But if you substitute minus t for t, the value of this function gets reversed. Therefore, any f of t can be split up into its even part and odd part respectively in this fashion. And when you do that, sometimes you will find some additional symmetries which are not present in the original waveform. Let us see how this goes. Suppose this is f of t, then let us construct what f of minus t would be. The sequence of values which this function takes for positive t, it will assume in the reverse direction. Therefore, you have corresponding to this and another loop corresponding to this on the negative side. And corresponding to this, you have a loop like this and it goes on like this. This is f of minus t. To get the even part of the function, then we have to add up these two waves and then divide by 2. So if you do that, then what you have is whenever this is blank, you have this half cycle of sine wave. Whenever this is blank, this is a half cycle sine wave you have got. Therefore, you have like this, where the amplitude now, the peak amplitude is a, but you are dividing by 2, this becomes a upon 2. And this is the even part of this. On the other hand, if you subtract f of minus t from f of t and divide by 2, you get the odd part, f of t minus f of minus t upon 2. So when you subtract the second waveform from the first, this gets reversed, the sign gets reversed, therefore this becomes a negative half cycle and this also becomes a negative half cycle, and therefore these negative half cycles fit in smugly into these blank intervals. And the result is that you have a waveform like this, which is a pure sine wave because each half cycle sine wave is reproduced in the proper direction here, and this is f of the odd part of t, f naught t. So now if you look at this constituent parts f e t and f naught t of your original f of t, you immediately observe that there are symmetries here. For example, f naught of t is certainly a pure sine wave, therefore there is no Fourier series expansion necessary for that. That itself constitutes the entire Fourier series, a naught by 2 sine omega. So this will be a naught upon 2 sine omega naught t. But as far as the even part is concerned, you observe that this has got what we described as a kind of half wave symmetry. The function repeats itself every half cycle. And you also recall that we mentioned in the last class, last lecture, that whenever you are having a waveform like this, we would like to still to continue this as the basic period, not as this, because we are going to relate this basic period to the parent waveform from which it is generated. After all, we want to talk about fundamental frequency in relation to this. Therefore, we will continue to have the same fundamental frequency when describing this waveform as well. Consequently, we regard this as the basic period, in which case the function f of t happens to be f of t plus t naught upon 2. Therefore, this will have only even harmonics present. And since the function is even, only sine terms, only cosine terms will be present. So if you make the Fourier series expansion of this and add to this the Fourier series expansion of f naught of t, which is this, then you get the Fourier series for the entire function. So let us do this. Fe of t, suppose, as a DC term, the average value of this, as you know, any sinusoid, we are talking about the absolute average value 2 upon pi, that is the DC term, plus you have an cos n omega t, where you need to have n even only, because odd values of n would be absent because it contains only even harmonics. To calculate an, you take twice the average of the function 0 to t naught f of t cos n omega naught. And it can be shown that the contribution coming from this integral for 0 to t naught by 2 will be the same from t naught by 2 to t naught, provided n is even. Exactly the same arguments which we used in discussing the half wave symmetry case, where we have odd harmonics present. Exactly the same way we can show that this is equal to 4 upon t naught 0 to t naught upon 2. That means we are taking the average of this function over half cycle, f of t cos n omega naught t dt for n even only. You see, this particular formula will not be valid for n odd. I will not go to the resulting integration. It can be shown that this will lead to minus 2a upon pi n squared minus 1, that is the value. So finally, the Fourier series expansion for this can be written. I will write it here. So the Fourier series for this waveform would be f of t equals the DC term a upon pi plus the fundamental term which comes from the odd part a upon 2 sine omega naught t plus the remaining terms in the Fourier series expansion of the even part of the function, which will be minus 2a over pi times n squared minus 1 cos n omega naught t for n even starting from n equals 2 onwards. So you observe that even though this function as such does not appear to have any of the symmetries that we have talked about, by splitting this up into even and odd parts, you are able to find some symmetry at least in one of those parts, and the other of course falls out. It just breaks down into a single term. So it would be sometimes worthwhile for us, before we proceed to get the Fourier series expansion of any waveform, to see if we can produce some symmetries by resolving this function into its various constituents, one of them being probably the even part and the odd part respectively. You can think of other ways of resolving this, but we need to confine our discussion only to this. Now let us use this work that we have done here to work out another example where such a waveform is applied to an electrical circuit. In this example, we will consider that a waveform of a voltage of this shape is applied to an RC circuit and the voltage across the capacitor is taken to be the output voltage. So we will imagine that the peak value of this half wave rectified sine wave is 100 volts. Now this voltage is applied across the RC circuit, and we are interested in finding out the significant harmonics both at the input and the output voltage. So the problem is find the amplitudes of the significant harmonics in Vi and the output voltage V0. The data that is given R, let us say, is 1000 ohms, C 15.9 microfarads, and omega naught corresponding to this period T naught is 100 pi radians per second, which means the fundamental frequency is 50 hertz. Now since this input waveform is not sinusoidal, we can't apply straight away the phasor methods for calculating the output voltage. On the other hand, the Fourier series tells us that such an input voltage can be decomposed into a number of sinusoids, and so for each one of the sinusoidal components we can find out the corresponding output using the phasor methods and superpose all the solutions to obtain the output. Or in the problem like this, we are only interested in knowing the magnitudes or the harmonic components in the output voltage V0. So for each harmonic we can apply the phasor notation and the phasor algebra. Now we know that Vi can be expressed by means of Fourier series using the formula, using the result that we have obtained in the previous example when we considered just this kind of wave, half wave rectified sine wave. The answer there was, if you substitute the numerical values, will turn out to be 100 upon pi, that is the DC component, plus 50 sine omega naught t, that is the fundamental, and in addition we have a number of even harmonics. The first two even harmonics are the second harmonic and the fourth harmonic. This will be 3 pi and this is 200 by 15 pi cos 4 omega naught t. So for each one of these plus other terms which are insignificant, which we will ignore. For each one of these we would like to find out the output, corresponding output quantity, and to do that we must find out the output voltage to the input voltage ratio as a function of frequency. So the system function in this case Hj omega by potential divider action is 1 over j omega C divided by R plus 1 over j omega C, that will be 1 over 1 plus j omega Cr. This is the general system function as a function of frequency omega, but we are interested in evaluating this for particular values of omega, which are omega naught 2, omega naught 4, omega naught, and so on. Consequently, we will find out H Jn omega naught for a general n. This will be 1 over 1 plus j n omega naught Cr, which when you substitute the numerical values for R, C and omega will turn out to be 1 over 1 plus j 5n. In particular, we are interested only in the amplitudes of the harmonics. So we are not really interested in the angle associated with h of j n omega naught. So we would like to know only the magnitude in our problem. This will be therefore the 1 over square root of 1 plus 25n square. So we know the amplitudes of each one of these harmonic terms. We know the magnitude of the system function. Now therefore we can find out the amplitudes of the output voltage. We can do it, we can organize it in this fashion. The amplitudes of DC, of course DC there is only one quantity, we don't have to talk about amplitude, but we can talk about the amplitude of the fundamental component, the second harmonic and the fourth harmonic. These are the significant harmonics that are present. So the input voltage has a DC component which is 100 upon pi, that is 31.8 volts. The 50 cycles component is 50 volts. The 100 cycles component is 200 upon 3 pi, that is 21.2 volts. And the 200 hertz component is 200 upon 15 pi, that turns out to be 4.24 volts. So these are the amplitudes of the different harmonic components as far as the input is concerned. And the value of the system function, when you apply a DC output input here, the same DC comes out across here because there is no current passing the circuit, and therefore that is equal to 1. The input output ratio is 1. In the case of the fundamental, n equals 1, therefore this is 1 over square root of 26. Case of second harmonic, n equals 2, therefore this will be 1 over square root of 101. And in the case of the fourth harmonic, n equals 4, so 16 times 25, 400, this is 1 over 401, square root of 400. So when you multiply these amplitudes with the corresponding magnitude of the system function, as far as the output is concerned, the various components will turn out to be this multiplied by this 31.8 volts. The 50 cycles component turns out to be 9.8 volts. 100 cycles 2.11 volts, and this is 0.21 volts. So this RC circuit here essentially acts as a filter. You have an input voltage which is non-sinusoidal, which is a rectified sine wave, half wave rectified sine wave, and we would like to have a filter like this to swamp out the ripples. So all the AC components should be reduced to the extent possible, and we would like to have the output to be as pure a DC as possible. Now how good is this filter? Let us see. In this case, in the fundamental, in the input we have 38.8 volts DC, but the harmonic components are quite substantial, 50 volts fundamental, 21.2 second harmonic, 4.24 fourth harmonic. But as far as the output is concerned, the harmonic amplitudes are brought down considerably compared to the DC. Therefore, this is a good filter as far as the suppression of the various harmonic components are concerned.